Electromagnetic induction. As the name suggests, electromagnet, that is, there must be some chemistry between the electric and the magnetic effect. So now let's start with the electromagnetic induction. In this chapter, we are going to study the various experiments and various laws associated with it. As we all know that when the current is passed through a conductor, then in that condition the magnetic effect is created around it. But when we revolve a conductor in the stationary magnetic field, or when the magnetic field is made to vary with respect to the stationary conductor, then in that condition the EMF is generated in the coil or in the conductor. What is this EMF? The EMF is the electromotive force, or you can say a voltage. If the voltage is generated, then in that condition the current flows in the conductor. So this is called electromagnetic induction. In other words, we can also study the electromagnetic induction as if there is a relative motion between the conductor and the magnet. So due to this relative motion between the two, the electromotive force is developed in the conductor. There are two famous scientists who proposed this law, the Henry and the Faraday. These two basically proposed that when the conductor or the magnetic field is varied with respect to each other, then the EMF is generated, which is called the electromagnetic induction. In this condition, the current which is developed in the conductor is called the induced current. This induced current is detected by the galvanometer. The galvanometer is a measuring device which has a needle in it. This needle shows deflection if there is the presence of current in it. That is, if the current is flowing in a circuit and the galvanometer is attached to it, then in that condition the needle shows deflection. If there is no current in it, then it shows no deflection. So in order to find out that the current is induced in the conductor or not, we are going to place the galvanometer in series with the conductor. Now let's start with a basic experiment that tells you in detail about the electromagnetic induction. In this experiment, we see that there is a coil which is wrapped in the form of helix. This coil acts as a conductor. To this conductor, the galvanometer G is attached. Now, take a bar magnet. This bar magnet has two polarity, that is the north polarity and the south polarity. In the first condition, we can see that when the bar magnet is brought near to the coil, then in that condition, the galvanometer shows a momentarily deflect. Now, if the bar magnet is moved away from the coil, then in that condition, the galvanometer is showing the momentarily deflection but on the opposite side. And in the third case, if the magnet is made stationary with respect to the coil, then the galvanometer shows no deflection. Now, why is it happening so? Let's understand. Through this experiment, we have drawn some observation. First observation tells us that when the magnet is brought near to the coil, in that case, the galvanometer is showing the deflection towards the left hand side. The second observation is that when the magnet is brought away from the coil, then in that condition, the galvanometer is showing the deflection on the right hand side. And the third observation is that when the magnet is kept stationary with respect to the coil, then the galvanometer shows no deflection. So there is a major concept behind it, and this concept is called electromagnetic induction. So now let's start with the conclusion of this experiment. Before proceeding further, we need to take a recall. We need to remember and try to recall the magnetic lines of forces. What are these magnetic line of forces? If I have to draw the magnetic line of forces along the bar magnet, then in that condition, these lines of forces start from the north pole and ends towards the south pole. These magnetic line of forces are the imaginary line which is built around the magnet. Now let's again see the experiment by taking the magnetic line of forces into consideration. In this case, the first case that we talk about, that when the magnet is coming near to the coil, then in that condition, the magnetic line of forces increases. The magnetic line of forces increases into the coil. These magnetic line of forces are called magnetic flux. So let's first understand what is this magnetic flux. The magnetic flux is basically the magnetic lines of forces in a particular area. That is, if the area is small, the magnetic line of forces passing through it is also small. That is, the magnetic flux is less. If the area is large, the magnetic line of forces passing through that area also increases. So, the magnetic flux also increases. In order to understand the magnetic flux, let's take a very small example. We have a window at home. Through the window, the light enters. Okay, if the window is small, then in that condition, the amount of light entering is also small. If the window is large, then the amount of light entering through that window is also large. Another example, you can say you have a sieve at home. Okay, the sieve is used to filter out the water from the solid or the liquid from the solid. Okay, so what happened that if the sieve is small, so the amount of filtering is also small. If the sieve is large, then the amount of filtering is also large. Same, you can connect these two examples with that of the magnetic flux. In the magnetic flux also, what is going to pass through the filter? The magnetic line of forces. The magnetic line of forces are going to pass through a particular area. So this is all about magnetic flux. You have to keep magnetic flux in mind because it is very essential for you to understand the electromagnetic induction. Now, as I've already told you, when the magnet is brought near to the coil, then in that condition, the magnetic line of forces in the coil increases. If the magnetic line of forces increases in a particular area, then the magnetic flux linked with the coil also increases. Now, you see that initially the magnet was far from the coil. But now the magnet is near to the coil. Okay, when the magnet is far from the coil, then in that condition, the magnetic flux is less. When the magnet is near to the coil, then in that condition, the magnetic flux is large. So due to this change in magnetic flux, the EMF or the current start flowing into the conductor. So in that condition, the galvanometer shows you the deflection because the galvanometer detects the presence of the current. Now in the second condition, when the magnet is brought away from the coil. Okay, now you see, when the magnet is brought away from the coil, the magnetic lines of forces into the coil decreases. That is, the magnetic line of forces decreases from higher value to lower value. So, the magnetic flux which is linked with the coil also decreases from higher value to lower value. Again, there occurs a change in magnetic flux. Due to this change in magnetic flux, again the EMF is generated in the coil which is detected by the galvanometer and the galvanometer shows the deflection. Now, the third is the case when the magnet is kept stationary with respect to the coil. In this condition, the magnetic lines of forces which are linked into the coil is constant. It is not changing. That means the magnetic flux which is linked with the coil is also constant. It is not changing. If there is no change in magnetic flux, so no EMF is generated and thus the galvanometer does not detect the presence of current. The change in the magnetic flux causes the EMF to be induced in the coil. And this statement is given by a very famous law which is called a Faraday's law. So, the Michael Faraday have given us a proper statement on electromagnetic induction that when there is change in magnetic flux which is linked with the coil, then the EMF is generated into the coil. In order to understand further, we have to go into a very basic and important concept. The concept is Fleming's right-hand rule. According to this Fleming's right-hand rule, there are three important specifications. The specifications are force, current and the magnetic field. The force, the current and the magnetic field are denoted by using the right hand. Okay, so this is my right hand. In the condition, if I have to notify the force, the current and the magnetic field, then I have to stretch my 3 fingers. These 3 fingers extend perpendicularly to each other. That is, the thumb should be perpendicular to my forefinger, the forefinger should be perpendicular to my middle finger. Now, in this condition, the thumb will point the direction of the force. That is, if my thumb is pointing in upward direction, then the force is also acting in upward direction. What is this force? This is the force which is exerted on the conductor, or this is the force which causes the conductor to move in a particular direction. Now this forefinger represents the direction of the magnetic field. Now the third finger, that is my middle finger, represents the direction of current. What is this current? This is the current which is flowing in the conductor. If my finger is pointing in this direction, then that means that the direction of current is from right hand side to left hand side. Because the arrow in which my middle finger is pointing, it shows the direction of current in this way. Okay, so towards left is the direction of current. My forefinger is pointing outward. That is, the magnetic field is created outward out of the plane. Now, these fingers of my right hand represent the Fleming's right hand rule. So, in order for you to understand that where the force is acting or where the current is acting, you have to take into consideration the Fleming's right hand rule. It will help you out to find out the direction in the AC generator, in the DC generator and so on.